Our next very important topic in complex numbers is Euler's formula, and Euler's formula basically relates the circular function sine, the trigonometric function sine and cosine to the exponential. And what it basically says is that if you have e to the power I theta, then that's equal to cosine theta plus I sine theta. Now there is a proof and derivation for this formula, and it comes from the Maclaurin series of sine x, cos x, and the exponential. And you need to look at the complex version of the Maclaurin series for complex numbers, and that's not really covered here. It's when you study complex analysis. The proof is rather straightforward. You can find it in many places. Even if you were to substitute e to the iz into the Maclaurin series of the exponential, it becomes quite clear that it's cosine x plus I sine x. Anyway, let's move on and let's try to see how this property now can be used. So as far as we're concerned, any complex number z, okay, any complex number z can be expressed as, if you recall, r can be written as cosine theta plus I sine theta. So this means that by Euler's formula now we are saying that the complex number can be written as REI theta. So this is a short notation. This is the proper exponential function. So all that we know about the exponential function can be used here to work with complex numbers. So in order to, of course, express something like, for instance, any number as any complex number in this form, we have to, of course, find its argument and modulus, and then substitute it into this, and that would do basically. So, for instance, if we had the minus 2 plus I, the modulus of minus 2 plus I is 4 plus 1, 5. So it's under root 5. Okay, it's square root 5, and the argument of minus 2 plus I is turns out to be 2.6779. 2.6779. I'll leave it to you to figure that out. So what happens then is, of course, minus 2 plus I can be written as square root 5 e to the 2.6779. So it can be expressed in that form. So we note that under the Euler's formula definition, we can clearly show that cosine of theta, in fact, turns out with a nice little combination is in fact this, divided by 2. Sine theta, similarly, is just ei theta minus e to the minus I theta over 2i. Okay, and these, if you will note, look very familiar to the hyperbolic functions. I'll write them down here on the side. Cos x, you will recall, is e to the x plus e to the minus x over 2, and sine x is e to the x minus e to the minus x over 2. So you can see the similarity in these two formulae. Okay. So if we combine these two ideas, we can see that, in fact, cosine hyperbolic of Ix, okay, imaginary times x, is equal to, in fact, just replace Ix into the formula of cosh, and you get e to the Ix, okay, e to the Ix plus e to the minus Ix, okay, and this is then divided by, according to the cosh formula, just a 2. And that, you will notice, is actually simply cosine of x, according to the definition that we have above here for cosine theta. So that clearly shows you that cos x, in fact, is cosh ix. Similarly, if we do the same with the sine, or sine hyperbolic, we end up with e to the ix minus e to the minus ix all divided by 2. Now, what you're missing in this case, of course, is the 2i, because if you look at sine I, all it means is if I multiply sine x by I would end up with the same thing. Okay, so this is a very interesting relationship between the trigonometrics and the hyperbolics. Okay, so the circular, if you like, and the hyperbolics. Right. In a similar way, we can easily show, okay, with very little manipulation from these definitions, in fact, we can show that tan hyperbolic of ix is in fact equal to I tan x. And this you can easily do by the definition of tan and tan hyperbolic, which is sine over cos, or sine x over cos x. And it's quite obvious and simple to prove. Okay. Here, one other form of a little bit of kind of interesting manipulation is that if we look at the cosine of z, clearly that can be written as cosine of x plus iy by definition. Using the sum to product identities, the sum of a and cosine of a plus b, using that identity, we can easily expand this, in fact, to cosine x cosine iy minus sine x sine iy. Now if we go back to our definitions just above here, we can replace the cosine ix, okay, by simply cos. Okay, just one second. Well, if we note here, using this kind of same arguments as here, we could very easily show that in fact cosine ix turns out to be equal to cos x, in fact. Okay, very simple to do that. Simply replace the ix, and the result pops out quite quickly. And in the same way, and all you have to do is to substitute, for instance, here ix, and that goes here, so this will become I squared x. Instead of x, you're putting in ix, so this will become I squared x. So these will become real then, okay? And of course, when it goes in here also, you will get the same. It'll be I squared x, which is minus, but it turns out by definition it's going to be cos x. And similarly, we can show that sine ix, okay, turns out to be, in fact, I sine hyperbolic of x. So we can use these results, in fact, here, and then cosine of z becomes cos x and cos y, okay, by the above, and then here we'll have minus I times sine x sine hyperbolic y. So in this way we can write it as the objective here is to have the real part and the imaginary part. So here's your real part and here's your imaginary part. Okay.